Hey everyone, and welcome back. We are finishing off this course by looking at our quicksort comparison and actually analyzing the algorithm by running it and counting comparisons here. So we have the same quicksort code that we had before. All three of those functions are here. You can watch me implement them in the previous video. But what we're going to really focus in on is different pivot choices. We will pick different values and move them into the last element in our array so that our partition can pick them up appropriately. Different pivot choices are going to result in different amounts of work, and we're going to measure that work, like I said, using a simple comparison counter. We're going to count how many times we actually do the check of, in our position right here, how many times we actually do this check right here. If A at J at our boundary, at our current scanning variable is less than our pivot, we need to do our swap, right? So we're going to keep track of the comparisons using this long counter. It's a static global variable, and we'll just increment it before we ever call that, like for each time that we end up calling that if statement. This should give us a rough approximation for how hard Quicksort had to work as part of the setup and data that we're going to feed through it. And the basic idea here is going to be more comparisons means more worked. Now, in merge sort, we always were splitting our array into two. And we were always splitting our array into two based on the length of our array or the subarray. And what this enabled us to do was get the robustness of two evenly distributed halves of an array. We lose that certainty with Quicksort. Quicksort does not depend on the size of the array. It depends on your pivot choice, which means we could end up with mighty unbalanced splits when we go to partition around a given value. Imagine for a second in an array that looks something like this, 0, 1, 2, 3, 4, 5, 6, 7, and I told you that my pivot choice was 1. We can see here now that we end up with two very different looking partitions. We have one partition on the left with literally no data in it, and one partition on the right with all the data in it. This doesn't happen in merge sort, but it does happen here. And balanced splits are incredibly important to reach that n log n runtime that Quicksort is supposed to give us, similar to what merge sort gives us. If we end up with consistently skewed splits, like the one I just showed here, we actually start to head toward n squared behavior, that quadratic formula, that selection and insertion sort worst case behavior. So that's pretty awful, which we don't have that problem with merge sort, given that it is always so balanced. So our pivot choice will influence whether our splits are balanced. And we are going to try 5 different pivot strategies. So I've got some code here that I'll show really quick around choosing a pivot. Depending on what pivot strategy, we can either choose the very last element in the array, we can choose the first element in the array, and again, in order for our partitioning algorithm to pick it up, we are going to just swap it, but whatever was the first element will now be, that value will become our pivot. There's the middle value that we could pick. There is a random value in our array, just pick a random value. And there's this little bit fancier version where we get the median of the lowest, the middle, and the highest value based in our array. So we take the first element, the last element, and the middle element, and we take the median of all 3. All right, to keep our partition code unchanged, each strategy, like I said, will ensure that the chosen pivot ends up at that high position, and then we can just run our same partition algorithm as before. I'm going to go ahead and just run this. We're going to get a big table printout, and then I'll talk about what the table is showing us, what it means, and sort of how we can interpret the results. So what we'll see is that I'm running over n equals 100. Each of these are our different pivot choices. These are the characteristics of the data in the array. So sorted meaning from lowest to highest, and then comps is the number of comparisons of that if statement that I previously highlighted. So on sorted input, what we can see is choosing the first or last value as a pivot is awful. This is because our partitions, as I showed in my example, become extremely skewed. We also see that the median of 3 and the random pivots usually avoid that bad luck that would happen. So we can see that these numbers are significantly lower at 480 and 659 over these comparison values at almost 5,000 each. Much like the sorted, the reverse sees very, very similar values, where unlike in insertion sort, where sorted was fine, reverse sorted was terrible, here any kind of sorting on our data, like pre-existing sorting, skews our data set, right? The distribution of our data is all messed up. And then our different partitions are all messed up. And if our partitions are messed up, it just trickles down. We end up with a skewed tree and we end up with almost n squared work. The best case scenario we can see, while these numbers are all a little bit higher than middle, random, and median of 3 choices, we can see that here, if we don't know anything about our data, but there's a chance it could be sorted, there's a chance it could be reversed, like we don't know, what we can see here is we can get a consistent number of comparisons if all we do is have random data, right? So if we're not really sure, what we see is picking a random value as the pivot is better than what we did originally, which was always picking the last. Or picking the middle value was always better than picking the last. In fact, while showing you the last was the simplest in the beginning, there's never a reason to just take that last element and make it your pivot, because in the off chance you do have sorted data, you're really messing yourself up. So picking something random is going to be even better. When our splits are balanced, the recursion that's occurring has about log n levels of work, very similar to our merge sort or our binary search. And each level can do that n work in partitioning. So we end up with that n log n algorithm that we are really hoping to get. But when our splits are skewed, our tree actually just becomes a big long chain of length n, where each one is doing n work in partitioning. And now we have n squared. This is why Quicksort usually beats simple quadratic sorts, but it doesn't have to necessarily beat other quadratic sorts if we do a really bad job of picking our pivot. The nice thing that we do get from Quicksort is that we are supposed to be able to avoid repeatedly comparing everything to everything else, the way that merge sort avoids this. Merge sort is reliably n log n, but it also used extra memory in the merge. We had to make extra arrays and move everything together, and that coordination was a lot trickier than writing up our Quicksort. Quicksort is in place, and it's pretty fast in practice, but as we've now seen, it can degrade if our pivot choices are consistently poor, and this is why our pivot strategies matter so much. Real libraries, most of the time, honestly will combine strategies. They have good pivot selections, and then they switch to insertion sort for tiny subarrays. We don't really need to ever do that hybrid for ourselves, and we don't need it to understand the core idea, but it is kind of neat to understand why production sorting and like the library-based collections.sort are so robust. Pivot choices affect balance, and that balance is what affects our recursive depth. If our depth is affected, then our number of comparisons are affected, and that, in turn, will affect our runtime. There are many people out there who are dedicated to figuring out fast and efficient and effective ways to do things like picking strong pivots, robust pivots, regardless of your data set. But hopefully this can really highlight the importance of not only knowing your algorithms and knowing your implementation details, but also getting to know the data set that you're working with and how all that information together can really start to paint a picture of what a computer scientist needs to do before they can actually even get their hands to keyboard. Thank you for taking this very long journey with me through all of these videos. If you've watched them all, thank you so much. These are my supplementary videos on top of my already existing course lecture material videos. And if you're looking for more, I have another subset of videos where I discuss individual practice problems, and I sort of try to solve them out loud and help people understand some of the intuition and thinking behind problem solving questions that like show up in interviews or exams and stuff like that. So thank you so much, everyone, and have a great day.